As with resistors, energy storage elements can be combined to form a single equivalent energy storage element. In this video, I'll show how to combine capacitors to form an equivalent capacitance and how to combine inductors to create an equivalent inductance. The order of the differential equation describing a system is the same as the number of independent energy storage elements in the system. Combining energy storage elements into fewer equivalent energy storage elements reduces the effort required to write and solve the differential equation governing the system. This process is a generalization of the circuit reduction techniques we use to combine resistances in Unit 2. You can combine capacitors that are in either series or parallel to form an equivalent capacitance, and inductors in series or parallel can be combined to create an equivalent inductance. The process of combining energy storage elements reduces the number of apparent energy storage elements, and thus the order of the differential equation governing the system. The benefit in doing this is significant, but as with resistors, be sure that you don't combine elements that shouldn't be combined. Make sure that the energy storage elements you're combining are in either series or parallel before combining them. No other configurations allow you to combine elements. Suppose we have a series combination of n capacitors, as shown here. Since the elements are in series, they all share the same current I of t. The voltages across each capacitor are defined here. If the voltage across the kth capacitor is 1 over C sub k times the integral of current I dt plus the initial voltage V sub k at 0, I can use this equation for the voltage across each of these capacitors. Now if I do KVL around this loop, that says that this voltage, V of t, is equal to 1 over C1 times the integral of I dt plus V1 at 0. So that's the voltage across capacitor 1 plus a very similar term for a bunch of other capacitors up to C sub n. Its voltage is going to be 1 over C sub n, integral of I dt plus V sub n at 0. If I combine these terms, V of t is equal to 1 over C1 plus 1 over C2 plus a bunch of other similar terms up to 1 over C sub n times the integral of I dt plus all of these initial voltages, V1 at 0 plus a bunch of other similar terms up to Vn at 0. The sum of these voltages is just this voltage at t equals 0. So this becomes V at 0. This looks like 1 over an equivalent capacitance times the integral of I dt. Capacitors in series can be combined into a single equivalent capacitance. From the standpoint of a voltage-current relationship at these terminals, this circuit is equivalent to this circuit, which has a single equivalent capacitance. I just have to choose the inverse of this equivalent capacitance to be the sum of the inverses of the individual capacitances in this circuit. Capacitors in series can be combined in much the same way as resistors in parallel. Invert the individual capacitances, add up the inverses, and then invert that result. For capacitors in parallel, all of the elements share the same voltage difference. I'll call that voltage V of t. However, I do need to define the currents individually for each capacitor. I'll call those I1 of t, I2 of t, and so on up to I sub n of t. The current through each capacitor is the capacitance times the derivative of the voltage difference. If I use that information and do KCL at this terminal, the current in to that terminal is I of t. That's equal to the sum of the currents leaving that terminal. This current, I1, is C1 dV by dt, plus the current I2 is this capacitance, C2 times dV by dt, plus a bunch of other terms, plus the nth capacitor is C sub n dV by dt. I can pull out all of the C's. So this becomes C1 plus C2 plus all the other capacitances up to C sub n times the derivative of voltage with respect to time. That can be expressed as a single equivalent capacitance CEQ times dV dt, which is the same voltage current relationship if I set CEQ equal to the sum of the individual capacitances. If I have n capacitors in parallel, I can combine the capacitors into a single equivalent capacitance. From the standpoint of a voltage-current relationship at the source terminals, this circuit is equivalent to this circuit with a single equivalent capacitance. I just have to choose the equivalent capacitance to be the sum of the individual capacitances. This means that capacitors in parallel are combined in much the same way as resistors in series. Just add up the individual capacitances to get the equivalent capacitance. Now I'll do a simple example of combining capacitances. These two capacitors are in parallel. Parallel capacitances add directly, so this becomes CEQ1 is just 2 microfarads plus 1 microfarad. It's 3 microfarads. Now this capacitance is in series with this 6 microfarad capacitance. Series capacitances add like parallel resistances, so CEQ is 1 over 6 microfarads plus 1 over 3 microfarads, which is just 2 microfarads. For the case of 2 and only 2 capacitances, I could also get this by multiplying 6 times 3 and dividing it by the sum of the capacitances. Now let's look at combining inductors in series. Since the circuit elements are in series, they all share the same current, I of t. The voltages across the individual inductors are shown here. Now if I do KVL around this loop and use the relation that the inductor voltages are equal to the inductance L times di by dt, I get this equation. The individual inductances can be factored out of this equation to get this one. Now, if I define an equivalent inductance as the sum of the individual inductances, this circuit has the same voltage-current relation as a single inductor with this inductance. Since inductances in series add directly, they're combined much in the same way as resistors in series. Finally, let's look at the equivalent inductance of this combination of parallel inductors. Since these inductors are in parallel, they all share the same voltage difference. I do need to define individual inductor currents though. The derivation of the voltage-current relationship for this set of inductors corresponds to the procedure for combining series capacitors. Just interchange the roles of voltage and current in that derivation. The result will be that we can represent this set of inductors with this single equivalent inductance. We just need to define the inverse of the equivalent inductance as being the sum of the inverses of the individual inductances. This formula corresponds to the formula for combining parallel resistances. So in some sense, parallel inductors are treated similarly to parallel resistors. Finally, I'll do an example of determining an equivalent inductance for this network of inductors. These two inductors are in parallel. They have an equivalent inductance, L sub p, of the product of the two over the sum of the two. So 6 millihenries times 3 millihenries over 6 millihenries plus 3 millihenries. Inductors in parallel add like resistors in parallel. Since there's just 2 of these, I can use the special formula for parallel resistances. This becomes 2 millihenries. Now this parallel inductance is in series with this 2 millihenry inductance. So LEQ is the sum of those two since inductors in series add like resistors in series, so the equivalent inductance is 4 millihenries. That covers the essentials of voltage-current relationships for energy storage elements. Next, we'll analyze electrical circuits that contain energy storage elements. But before we do that, I'll talk a little bit about the fundamental differences between circuits that store energy and those that contain only resistors.